Leah here from leahforsyth.com/MCAT, and in this video, we're going to look at conventions for writing chemical equations. Chemistry is all about the reactions, but when you're given a reaction, such as this precipitation equation, what exactly are we looking at? Every number, every letter, every symbol has a very specific purpose and is very important. Let's look at one more. The dissociation for acetic acid, same set of symbols going on, but a little bit different. So let's break it down. When you look at a reaction equation, you'll see some sort of arrow in the middle. That's going to separate the start of the reaction and the end of the reaction. Whatever you see on the left of the reaction arrow, no matter what the arrow looks like, those are called the reactants. The reactants react either with themselves or with each other to give you what we get on the right side of the equation, which are your products. Products are the result of your reaction. You'll notice that we have a small letter or letters after each reactant, and this refers to the phase or the physical state of what's reacting. You should know your three phases of matter, starting with solid, written as a lowercase s. This is something with a definite shape and size that you can see, that you can touch, like a book or a table. Liquid is a lowercase l. Liquids take the shape and size of their container, but they have a definite volume. For example, water can take the shape of a tall glass or a bowl. And gas, lowercase g, does not have a definite shape or volume, and that means it can expand to fit its container. For example, you can have oxygen in a tank, but if the tank leaks out, then the oxygen will just disperse into the environment. You'll also see one more physical state, and that is aqueous, written as lowercase aq in parentheses. Aqueous refers to something that is dissolved in aqua, in water. For example, if you have a salt like NaCl, it's solid, you can touch it, but if you dissolve it in water, it appears to disappear. And that's because the ions break apart so that sodium and chlorine no longer interact with each other, but instead they interact with the aqueous or water solution. In our precipitation reaction, you'll notice that calcium chloride and potassium carbonate are both aqueous, to form potassium chloride, which is aqueous, and calcium carbonate, which is solid. In our acid dissociation reaction, we have aqueous acetic acid dumped into a liquid solution of water, and when that happens, the acid dissociates to give us the aqueous hydronium ion and an acetate, which is an aqueous conjugate base. If you look at the product in the first reaction, there is a 2 in front of the KCl, but none of the others have such a number. This number is called the stoichiometric coefficient, or simply the coefficient. The coefficient tells us how many of that species are going to react. But it doesn't tell us the number, meaning if there's a 1, it's not that one molecule and that's it reacts. Instead, it tells us the ratio. But if most of the reactants and products don't have numbers, how many react? That's a trick question. If you don't see a number in front of the reactant or product, it's not that there's 0, it's that it's understood to be 1. But since so many reactions involve just one of something, we keep that one invisible to keep things simple. But in reality, for the first reaction, we have 1 calcium chloride reacting with 1 potassium carbonate to yield 2 potassium chloride and 1 calcium carbonate. But that doesn't mean we have 1 single calcium chloride reacting. Remember, we said it's a ratio. When you carry out these experiments in lab, you'll have them in a test tube, a beaker, or a flask. Say we fill up this Erlenmeyer flask with water, and then we add in some acetic acid. It's not 1 single acetic acid that we dump into solution. Every drop has millions and millions of molecules because they're so tiny. So the coefficient numbers simply tell us for every one of this, 2 of that. For every 1 of calcium chloride, we will require 1 potassium carbonate, and this is where balancing equations comes into play, which we'll look at in the next video. In the second reaction, for every 1 acetic acid that reacts, 1 water molecule will be consumed and turned into 1 hydronium for every acetate that we produce. The coefficient is not to be confused with the smaller numbers that we see within the reactants and products. These numbers simply tell us how many of the atom or ion are reacting. When we look at calcium chloride, we have 1 calcium bound to 2 chloride ions to make a neutral salt. Potassium carbonate, we have 2 potassium ions for every 1 carbonate to make a neutral salt. The numbers in acetic acid, which is formed by covalent bonds, simply tells us how many of each are present. You can sometimes see this written as C2H4O2. You'll even see it as C2H3O2H, which is separating the acidic hydrogen from the remaining hydrogens. But at the end of the day, it's just about how many there are. 3 hydrogens bound to the first carbon atom, 2 oxygens bound to the second carbon atom, and the acidic hydrogen sitting at the end. Carbonate is a polyatomic ion, and in this case we're only using 1. But in some reactions, the molecule will require more than 1 polyatomic ion, adding another version of this number. For example, if I have the polyatomic ion calcium hydroxide, notice this looks a little bit different. What we have here are parentheses around 2 atoms to show us that these atoms are grouped together, and you'll see this when you need more than 1 polyatomic ion. The ion in this case is hydroxide, which is OH-, and since calcium has a charge of +2, we need 2 of the negative hydroxides to balance it. Putting that 2 outside of the parentheses tells us that it's 2 of everything within. 2 hydroxides means 2 of the oxygen and 2 of the hydrogen, and the parentheses tells us only apply the 2 to everything within. Even more confusing can be something like calcium nitrate, because now we have numbers inside and outside the parentheses. This is because nitrate is NO3-. There are 3 oxygens bound to the nitrogen to give us that negative charge, but that -1 is not enough to balance the +2 calcium, so we need 2 of them, and the 2 outside tells us that there's 2 of everything inside, meaning we have 2 nitrogen and 2 times 3 oxygen, which is actually 6. Again, something we'll look at in detail in the balancing videos next. Another thing you'll notice are pluses and minuses. When you have a plus in between 2 reactants or 2 products, it tells us that there are 2 different things. In the first reaction, we're told that calcium chloride reacts with potassium carbonate. That plus tells us calcium chloride and potassium carbonate react. The plus on the product side tells us we have 2 products. Potassium chloride forms in addition to calcium carbonate. This is not to be confused with the positive that I have here and the negative that I have here. If the positive and negative is sitting directly above a molecule or above an atom, then that's telling us that there's a charge. If it's sitting separate, it's telling us that we have one and the other. Hydronium is a positive polyatomic ion. The charge is +1, and so that plus tells us the charge. Not seeing a number tells us there is an invisible 1, and that gives us H3O+. For acetate, we don't have a number after the negative. That means there's an invisible 1, telling us that acetate has a charge of -1. What about the other reactants and products? If there's no number given, assume that it's neutral, because in this case, it's an invisible 0 rather than an invisible 1. Why is it an invisible 0? We're up to now lacking a number implied 1, for example, the coefficient or the charge. This is because with charge, it has to be plus or minus. And if we have an invisible positive charge, we still need the plus. If we have an invisible negative charge, we still need the minus. But if there's nothing there, it's not negative, it's not positive, it's neutral. So the invisible charge is 0, telling us that it's neutral. Finally, we have the arrows in between the reactants and products. The arrows tell us what is happening in the reaction, and the arrow reads as yields. So A plus B arrow C plus D means A plus B yields or results in or forms C plus D. You'll see many different types of arrows in chemistry and organic chemistry, but here are the most common types you'll see in reactions like this. If you see a one-way arrow going from left to right, this means that the reaction goes to completion. The MCAT requires you to memorize a handful of strong acids and bases. a list of which you can find on my website, layerforsci.com/reactions. And what sets them apart from the weak acids and bases is that the reaction goes to completion. The strong acid HCl, if dissolved in water, will break apart to give us H+ and Cl- near 100%. This means that all of the hydrochloric acid dissociates, and if there's none left, the reaction went to completion. On the other hand, weak acids, as we see here, do not go to completion. Instead, the reaction will find some sort of balance, where the reactants will go to products, products will go back to reactants, and this will happen back and forth at some specific ratio based on its dissociation factor. To show that it's going back and forth, we'll have arrows pointing in two directions. This is called an equilibrium reaction, where there is an equilibrium or a balance between reactants going to products and products going to reactants. And typically, instead of a full arrowhead, you'll see it as just top half or bottom half of the arrow. And sometimes, especially in typed text where they don't have this symbol, they'll draw two arrows like this. Say we have an equilibrium reaction where A and B are in equilibrium, or C and D are in equilibrium. We don't always have an exact A to B, B to A. Sometimes we can say that a reaction is product favored, where even though they're in equilibrium, it tends to weigh heavily in the direction of the products. You'll see this as the equilibrium arrows, but a bigger arrow towards the favored direction and a smaller arrow towards the less favored direction to show that you're favoring the products. Or, let's say C plus D is in equilibrium, but the reactants are favored. We'll have a bigger arrow pointing to the reactants and a smaller arrow pointing to the products. If the equilibrium arrow brought the double-headed arrow to mind, this is not typically seen in chemical equations, but you've seen it in organic chemistry during resonance. Resonance is less of a reaction and more about showing that a molecule is adopting two different states. For example, if we have something like this with a carbocation, we know that the pi bond can move over to the left. Now we show the double-headed arrow. The pi bond is now on the left and the carbocation is on the right. The double-headed resonance arrow implies that it's constantly going back and forth. And for resonance, you also have brackets around the two hybrids to show that it's really an in-between of the two, rather than a reaction that is taking place as we've seen above. You'll see many different types of chemical reactions on the MCAT, but that's a topic for another video. First, if you like this video, make sure to give it a thumbs up, then click the subscribe button and bell icon so that you don't miss any of the new videos. Then visit my website, layerforsci.com/reactions, for the complete stoichiometry video series along with the practice quiz and cheat sheet. The link again is layerforsci.com/reactions.